In this video, we're going to talk about other kinds of limits. So if you remember in the first video, we talked a bit about secant and tangent lines, and then we finished up lesson 1 with an introduction to limits. So by the end of this lesson, you should be able to answer the following little question. What are some other kinds of limits and why are they necessary? And just as a reminder, by the end of Unit 1, you should be able to answer the big question, how do we find the slope of a line using only one point? Okay, so let's get started today with the warm-up. So in class, you would do this by yourself. So we'll go through this really quick. A function is continuous if you can draw it without picking up your pencil. So a continuous function might be something like this. So notice to draw that function, I did not have to pick up my pencil. A jump discontinuity occurs when there is a vertical gap between different parts of a function. So something with a jump discontinuity might look something like this. So we have one branch that ends in a closed circle and another branch that ends in an open circle. So we couldn't have two closed circles because then we wouldn't have a function because we'd have one x value with two different y values. But as long as we have one open circle and one closed circle at some x value and those are split up, that gives us a jump discontinuity. Okay, so now looking at the graph of f of x below, how can we find the limit as x approaches 1 of f of x? So if we're looking at 1, x equals 1, that's right here, we notice that there's a jump discontinuity. So if we think back to lesson 1 and we think about how we were finding limits, limits were y values. Okay, so if we were going to look at this graph and let's say we want to come in from this side here, so we go along the curve, we're going to be approximately at 1 by the time we get to x equals 1. So we're never actually going to get there. We're never actually going to get to y equals 1, but we're going to get arbitrarily close. Okay, but if we come in on the other branch, we would be really close to 2. So the y value at x equals 1 when we're traveling along the right branch is 2. Okay, so this is a problem. We get two different values. So the solid circle is 2. And the open circle is 1. So since we have two different values, we can't really decide on one value to give to the overall limit, and that's a problem. So we can't define the limit as x goes to 1. Okay, so this is an important idea of approaching from either the left side or the right side and using that to determine if there is a limit overall. So what we want to talk about now is what's called a one-sided limit. So that's kind of what we were talking about just there, approaching from the left or approaching from the right, but not necessarily having a limit altogether. So a one-sided limit is the y value of a function approaches as the x value approaches a number a from either the right or the left of a. So not like in lesson 1 where we had something on both sides of the number we were approaching. Now we're just looking at one side at a time. And sometimes those sides might match up and you might have a limit overall from both directions. But if that's not the case, now we can actually define a limit for the right side versus the left side. So just a note on notation. The notation here is exactly the same as in lesson 1 for limits. So we have that LIM again with x going to a number, and then we have our function equals L. So again, this means the limit of f of x as x approaches a is L. Now the difference here, you notice, is on that number we're approaching, we're either going to have a little plus sign or a little minus sign. Okay, and what that tells us is which side are we approaching from. So plus means that you're approaching from the right, and minus means you're approaching from the left. Okay, so you can also think of it as plus means we're approaching from numbers greater than a, and minus means we're approaching from numbers less than a. So maybe let's jot that down really quick. So plus means numbers greater than a, minus means numbers less than a. Okay, so that's a one-sided limit. So let's do some practice. We're going to use the graph of f of x below to explain why each of the following statements is true. Okay, so if we look at statement A, we have the limit of f of x as x approaches -1 from the left is 1. So let's look at x is equal to -1, so that's right here. And if we want to approach this from the left, we need to decide which branch of the function we're looking at. So the left is over here. So if we're approaching from the left, what I'm going to do is travel along this little branch right here and see where my function gets really, really close to as I get really close to x is equal to -1. And we see that the y value there is 1. So we say at x values really close to -1, but not equal, or sorry, but less than -1. The y value is really close to 1. Okay, so very similar to the explanations we had in lesson 1, except we've got that idea of either we're coming from the left or from the right, and we're not thinking about both directions at one time necessarily. Okay, if we look at part B, the limit of f of x as x approaches -1 does not exist. Okay, so B is a little bit harder because we're going to have to think about both sides at one time. So let's look. So we know that the left-hand limit is 1. The right-hand limit would be if I travel along this little parabola shape down here, and we see that that's going to be 0. So the limit cannot exist because we have that jump discontinuity at x is equal to -1. So the way we explain that is we say the right-hand limit as x approaches -1 is 0, but we said in part A that the left-hand limit was 1. So these are not equal. Okay, let's look at part C. So now we're switching to our limit notation from words. So we have the limit as x approaches 1 from the left of f of x is equal to 0. So if we look at x is equal to 1 and we travel along the function from the left, so numbers less than 1, we'll be traveling along this little parabola shape, and we notice that indeed that's 0. So what's happening is at x values really close to 1, but less than 1, the y value is really close to 0. Okay. And finally, let's look at part D. So part D says the limit as x approaches 1 of f of x does not exist. So when we want to say does not exist, sometimes we abbreviate with the letters D and E. You'll see that a lot. Okay, so let's check this out. So we know the left-hand limit from part C. So let's look at the right-hand limit. Okay, so if I travel along this little piece of the function from the right all the way to x equals 1, I notice that I'm really, really close to 2. But that's not the same thing as 0. So once again, we have this jump discontinuity here where the function kind of starts at one value and leaps up to another value. And so we can't define one single limit there. So the way we explain this is we say the right-hand limit as x approaches 1 is 2, but we said in part C that the left-hand limit was 0. So these are not equal. Okay, so hopefully that's a little bit of an introduction to one-sided limits. So remember, same sort of idea as lesson 1, except now we're isolating those directions. So either we're coming from the left or we're coming from the right. Okay, so now we're going to look at a different kind of limit. We're going to start off with a little recalling from maybe some previous classes. So the domain of a function is its set of allowed x values. So for example, we could say the domain of f of x is equal to sine of x is all real numbers, so we'd write that negative infinity to infinity. The domain of f of x is equal to 1 over x is everything except for 0, because 0 would make the denominator 0. So we'd say negative infinity to 0 union with 0 to infinity. And then we could also say the domain of f of x is equal to the square root of x is everything 0 or bigger. So we could say 0 to infinity. Now, of course, you could come up with many other examples of domain. These are just 3 of your most common types. So either you might have something with all real numbers, or you have something that skips a couple numbers because they make the denominator 0, or maybe you have a root where you just can't have negative numbers. So even roots, you can't have negative numbers in the domain. Okay, so where are we going with this? Well, a vertical asymptote is a vertical line that the graph of a function is not allowed to touch. It corresponds to an x value that is not in a function's domain because it makes the function's denominator 0. And another name for this is an infinite discontinuity. So as an example, let's take the function f of x is equal to 1 over x minus 1. So the vertical asymptote is going to be the line where the denominator is 0. So if we look at the denominator, we see that it's x equals 1. And so if we think about what number makes that 0, well, if we plug in 1 for x, it would make x minus 1 equal to 0. So we know that x equals 1 is the vertical asymptote of this function. So as a picture, we could draw a vertical line at x is equal to 1. Maybe I'll label it down here. X is equal to 1, and that's the vertical asymptote. And then my function, 1 over x minus 1, is going to be a lot like 1 over x. So we're going to have something that looks a bit like this. It's just been shifted over. Okay, so if that's unfamiliar to you, make sure and go back and review function transformations. So f of x would be both of these little blue branches that we see here. Okay, so one thing to note, when you're drawing graphs by hand, asymptotes are always drawn as dotted lines. So let's make a note of that. So asymptotes always drawn as dotted lines on a graph. This is important because this is a lot different than if you graphed an or if you graphed a function like this on a computer or a graphing calculator. Either one of two things might happen. Either it may not show you the asymptote at all, and you might just see the function kind of disappear at some point, or it might show the asymptote is like a little piece of a solid line, but we really don't want to do that because when we draw it solid, it acts like it's part of your graph, but it's really not. It's like an imaginary line that's there, that's like it's a buffer for your function. Your function can't touch it, but it's not actually part of your function. So when we're doing this by hand with a pencil, always do it with a dotted line. Okay, so again, where are we going with this? Well, let's look at something with a vertical asymptote and think about limits. So if we look at the graph of f of x below, how can we find the limit as x approaches 0 of f of x? So if we look at x is equal to 0, that's the y-axis right here. And so we notice that this is acting as a vertical asymptote for the graph. So what's happening here is, remember, limits are y values. So what's happening to the y values as I get really, really close to this asymptote is they never settle on one particular number. They're always getting bigger and bigger and bigger and bigger. So I'm going up and up and up all the way to infinity. And so you might ask, well, could that be my answer? So yeah, turns out it can. So here it makes sense to calculate a limit because both directions are going up. So we can write that down. So it makes sense to calculate the limit as x goes to 0 of f of x because both sides of the function point up, and both directions increase forever. And the way we say increase forever or increase without bound is it goes to infinity. So we might say that the limit as x goes to 0 of f of x is equal to infinity. Okay? So turns out this is another kind of limit. So all of that recall, this triad example, this is all leading up to our next type of limit, which is an infinite limit. So an infinite limit means the y value of a function either increases, which would be infinity, or decreases, which would be negative infinity, without bound as the x value approaches a number a. In other words, you have a vertical asymptote at an x value, and either your graph points up or it points down. So let's take a quick look at notation. You can see it's the same exact notation that we've been using in both cases. It's just now your answer could be infinity or negative infinity. So it doesn't have to be a finite number. It can just be this general idea of up forever or down forever. Also, one important thing to note is we can combine this idea with one-sided limits. So here I didn't put any plus or minuses on the little x going to a in both of these. However, we could think about just one side, the left side or the right side of an asymptote at one time. Okay, so definitely just because you have an infinite limit doesn't mean you have to think about both sides. You can definitely have a one-sided case of an infinite limit as well. And we're going to see that in the next example. So use the graph of f of x below to find the following limits. If a limit does not exist, write does not exist, or D and E. Okay, so this is where we're going to start to see these combinations of our two types of special limits so far. So the first one we want to look at is the limit as x approaches -1 from the left of f of x. So we're looking at that one right there. So let's look at x is equal to -1. So that's this asymptote right here. And on the left side of the asymptote, we're going to be looking at this part of the function right here. So if we look at what that's doing as it approaches the asymptote, well, it's just going up forever. So this one would be infinity because it's increasing without bound. Okay, if we look at this one, so the limit as x approaches -1 from the right of f of x, we're going to be looking at this piece of the function down here, and we see as it approaches that asymptote, it's going down forever. So this one would be a negative infinity. Okay, so those were two one-sided infinite limits. So if we think about what's the overall limit, so the limit as x approaches -1 of f of x, well, we don't have one because on one side it's going up forever and on one side it's going down forever. So in some sense that's even worse than having this jump in your graph because that jump is infinitely large because you have something going infinitely high and infinitely low. So there's no chance we're ever going to have a limit there. Okay, so let's try this again and let's then look at this asymptote over here. So we're looking at x is equal to 5. So as the limit as x approaches 5 from the left means that we're going to look at this piece of the graph and on that side of the asymptote, and it's going down forever, so we're going to call that negative infinity. And then we have the limit as x approaches 5 from the right of f of x. So again, that's going to be the right side of the asymptote, and that's that part of the graph right there. So that's going up forever, so that's going to be infinity. And once again, our last job is to look at the overall limit, which again cannot exist because the left and the right are two different things. One is going up, one is going down, so this overall two-sided limit does not exist. Okay, we're going to talk about one more kind of limit in this video. So we talked about jump discontinuities, we've talked about infinite discontinuities, and those were vertical asymptotes. So if we talked about vertical asymptotes, we can definitely talk about the other direction, which is horizontal. So a horizontal asymptote is a horizontal line that the graph of a function is not allowed to touch at very large values of x. So horizontal asymptote is a little different than a vertical one because the function can actually cross it, just not when x is like 1,000,000 or 1,000,000,000 or 10,000,000,000. So it might cross it very early on in your graph, but as it goes out toward infinity or negative infinity, if it's a horizontal asymptote, that's when it should settle on this line and never touch it. Okay, so as an example of that, let's look at f of x is equal to x minus 1 over x plus 2 times x plus 1. All right, so this is going to have two vertical asymptotes because, well, actually, let me write the function over on the other side so we have room to see the graph. So we have f of x is equal to x minus 1 over x plus 2 times x plus 1. So our two vertical asymptotes are going to be at -2 and -1 because those are the two numbers that make the denominator 0. So those are my two asymptotes there. This is x is equal to -1. This is x is equal to -2. And then my graph looks something like this. So we've got a one branch going like this, and it's approaching the x-axis as a horizontal asymptote. So I'm going to make a little note of that, maybe in a different color. Well, no, it should be fine. Okay, so we're going to say horizontal asymptote is y is equal to 0. And these two down here are vertical asymptotes. So the middle part of the graph looks a bit like a parabola, except it's approaching those two asymptotes on either side. And then one branch here kind of goes up, and then it comes back down, and then it settles on that x-axis. Okay, so it's important to note about this particular function. I chose this on purpose because you notice we do have this little area here where it crosses the x-axis, but that's okay because way out here, where we're concerned about by infinity, it does in fact settle on that x-axis. Okay, so that's what we're worried about with a horizontal asymptote. So let's make one quick little note of that. So if we point like right here, f of x is allowed to cross a horizontal asymptote at small x values. Okay, and once again, we always draw our asymptotes as dotted lines. So let's make one more note of that. Asymptotes always drawn as dotted lines. Okay, so where are we going with horizontal asymptotes? Well, if you're guessing it's going to be another kind of limit, you would be correct. So a limit at infinity, this is going to be our last kind of limit today. A limit at infinity means the y value of a function approaches a number L as the x value either increases or decreases without bound. Okay, so in the infinite limits, our answer could be infinity or negative infinity. In the limits at infinity, it's our x value that's going to infinity or negative infinity. And our y value is typically a number. Now, that's not to say your answer here could definitely be an infinity or a negative infinity as well. And you'll see that in a couple of the exercises after the lecture lesson, that we could have combinations of limits at infinity with infinite limits. So your answer and x can both go to infinity. Okay. A little note on notation, still the same notation, just notice here it's x that's going to infinity or negative infinity, and that means that x increases or decreases without bound. Okay, but let's just remind you here. So we can have infinite limits at infinity. So as an example, that would be something like y is equal to x squared. So we know that that's a parabola, and that has no asymptotes at all. So really what's happening there is we would say something like the limit as x goes to infinity of x squared is actually equal to infinity. Okay. Those, we're going to worry about not combining types of limits just right now. We're going to work on limits at infinity by themselves. So for our last example, we're going to use the graph of f of x below to find the following limits. So just for your trivia here, f of x in this graph is equal to the inverse tangent function. So it might have been a minute since you've seen a graph of that. If it's been a while since you've had pre-calculus, or that was at least probably last year for a lot of people. So this is the graph of the inverse tangent function. We have two horizontal asymptotes. One of them is at y equals pi over 2. So I'll write that a little bigger. And one of them is at y equals negative pi over 2. And the graph goes on forever and ever and ever and gets really close to those two asymptotes. Okay, so the first one we want to look at is the limit of f of x as x increases without bound. So first of all, let's translate that into symbols. So we have the limit, I can write that better, the limit of f of x as x increases without bound. So we're looking for the limit as x goes to infinity of f of x. Okay, so for that, we want to look at values way out on the x-axis, so somewhere way out here. And we notice that that's approaching the asymptote that is at y equals pi over 2. So the answer to this limit would be pi over 2. Okay, now in part B, we have the limit of f of x as x decreases without bounds. So just like part A, let's go ahead and translate into symbols. So we have the limit as x approaches negative infinity of f of x is equal to. Okay, so if we look at negative infinity, remember that's just going in the other direction from the one we did in part A. So that's going to be over here. So at those really, really large negative values of x, we're getting really close to that horizontal asymptote of y is equal to negative pi over 2. And so that would be the answer to our limit. Okay, so the last thing you need to do in lesson 2 is just go through this check your understanding prompt and make sure to answer the little question, what are some other kinds of limits and why are they necessary? So just answer this in 2 to 3 questions, and that's the end of lesson 2.